In this video, we're going to discuss the central limit theorem as it applies to sample means. So first thing we need to talk about is something called sampling distributions. Now, I actually have right down here a great video that I would recommend you go watch before we even kind of get going. Like pause right now, go watch this video. It's such a good video on sampling distributions. And it kind of helps explain far better than me going through the definition with some really great visualization and examples. Okay, but we're also going to use something called the central limit theorem. And this says that if you draw a finite samples of size n from a population where we know the mean and the standard deviation, and we collect enough of these samples, then the resulting histogram is going to be bell-shaped. So what we're basically saying is that sample sizes that are at least 30, okay, should basically come from something that's normally distributed. So if we have a sample that's bigger than or equal to 30, that implies we're looking at something that is normally distributed by the central limit theorem, which they often abbreviate SLT. I'm sorry, CLT. So we can use that fact to allow us to look at a sample, and then because we can assume it's normally distributed, that means that we get to use that table for z distributions, because this only works when we're talking about normal distributions, things that are bell-shaped. So we're going to kind of use that fact to help us look at probabilities then for samples using the z-scores and those relative probabilities from the table. So before we do that, let me go ahead and give you the definition of a sampling distribution. So if you draw random samples of size n, the distribution of the random variable x bar, which consists of sample means, is called the sampling distribution of the mean. And it can be approximated using a normal distribution where the mean is the same as the population mean, which is stated right here. The mean is the same as the population mean. And the standard deviation is the same as the population standard deviation divided by the sample size, square root of the sample size. So here's what this is talking about. If you were to go out and find a sample and you were to look at its mean and compare it to the population mean, and let's say you do this over and over again, basically you create a bunch of data that you're looking at, which happens to be the means of samples. So this distribution is based on the means of samples. And that's where we're kind of coming up with this idea of the sampling distribution. But go watch that video, and I think that'll be a good use of your time to understand what the sampling distribution is. But we're going to apply this to some problems. So let's go ahead and look at an example. The length of time in hours it takes an over 40 group of people to play one soccer game, that's insulting, match is normally distributed with a mean of 2 hours and a standard deviation of 5.5 hours. Sample size of 50 is drawn from the population. Find the probability that the sample mean happens to be between 1.8 to 2.3 hours. So what they're asking is the probability that the sample mean is between, actually here, we'll write it with the other notation, 1.8 and 2.3 hours here. I won't put the equal to bar. It really doesn't matter though, when we're doing probabilities, if it's equal to or not. That doesn't make a difference in calculating the probability. So this is what we're looking at. So notice that the thing that I wrote different is that the mean, the sample mean, is going to be between 1.8 and 2.3. So normally when I'm doing a probability, I find a z-score. Well, I'm going to do that here, but this time my mean, which they say for the population is 2 hours, and the standard deviation for the population is 0.5 hours. When we're talking about taking sample means, this is not the mean and the standard deviation we'll use in our z-score formula. So our z-score formula, we're going to use our sample mean, and we're going to find the mean of the sample means and divide by the standard deviation for the sample means. And what I'm referring to there is this mean and standard deviation formula up here. So the mean happens to be the same, but the standard deviation is different. The standard deviation is the population standard deviation divided by the square root of the sample size. So in this problem, the sample size is 50. So we're going to figure out then 0.5 divided by the square root of 50. Now I'm going to plug that into my calculator. And I am getting 0.0707. So I'm going to go ahead and use 4 decimal places. I always like to use extra whenever I'm rounding. So because this number didn't come out nice, 4 or 5 decimal places is a safe idea. Okay. Okay, so there is my standard deviation. And now I'm going to find the z-score using that standard deviation. And then this is going to be the same mean. So the population mean and the mean for my sample is going to be the same. Okay, so the sample size that we took, or I should say that we're looking at, is we're wondering if when we go take our sample, if we happen to get either a number between 1.8 and 2.3. So we're going to have 2 z-scores. One is going to be based on the 1.8. So that's going to be 1.8 minus 2 over 0.0707. So that's the first z-score I'm going to find. And 0.0707. All right, so I'm getting negative 2.83. And the second z-score is going to be 2.3 minus 2 over 0.0707. So for that one, I am getting a much higher one, 4.24. Okay, so here's what I'm going to do. What I am looking at right now, I'm going to go ahead and draw a picture because I like to draw pictures of these, is I'm finding the probability that this is going to be between 2 z-scores, between negative 2.83, which is way out over here, and 4.2 something. Go ahead and extend that. 4.23. So I'm finding the probability between these 2 values. So when I want to find a probability between 2 values, I'm going to look up both of their values on the table, and then I'm going to subtract them. So for the first one, negative 2.83, let's see, 0, 1, 2, 3. So that's the first one, 0.00233. And for 4.24, 4.24. Okay, they don't even have a 4.24. So I'm going to go ahead and use the largest number possible, which is 0.99998. 99998. So that's what you do if it's not on there. Just use the biggest one possible. Okay, so I'm going to subtract these. 99998 minus 00233. 00233. Okay, and I am getting 0.99765. 9765. And that is the probability that this is going to happen, that we get a sample that's between 1.8 and 2.3 hours for an over 40 soccer match. So we're still working with z-scores. We're still working with the normal distribution, and we're still working with the table like we did in chapter 6. The difference is we're going to adjust our standard deviation because we're no longer talking about just any old data value. We're talking about a mean of data values, and therefore our standard deviation is going to be smaller. So we're looking at a smaller, closer together group because we're taking a mean. It's going to be even closer to the actual mean than just a regular old data value. Okay, so let's try another one. Let's see, in a recent study, that's not very recent, that's almost 10 years old, the mean age of tablet users is 34 years old. Suppose the standard deviation is 15 years. Take a sample of size n equals 100. So what would the mean and the standard deviation for the sample mean of ages be? So they're talking about doing a normal distribution with the mean and the standard deviation based on the mean and the adjusted standard deviation. So the mean is going to be the same mean as the population mean, which is 34. The standard deviation, however, we have to actually take the population standard deviation and divide it by the square root of the sample size, which in this case they said was 100. So that's going to be 15 divided by 10, which is 1.5. So that would be the standard deviation. So what does the distribution look like? What they're talking about is, is it symmetric, bell-shaped, right? Is it left skewed, right skewed? And here's where we're going to use the central limit theorem. So because our sample of 100 is way bigger than 30, we can go ahead and say it's normally distributed, or bell curve or bell-shaped. It's normally distributed by the central limit theorem. Oops. Okay, so now they ask us to find the probability that the sample mean is more than 30. So the probability that the sample mean is bigger than 30. So now we're going to be using a z-score again. But this time, we're going to use the standard deviation and mean that we found here in part A. So z is going to be 30 minus 34 divided by 1.5, which I'm getting 2.67. You might remember we round these to 2 decimal places, so when we look it up off the table, it's easier. I'm going to go ahead and draw a picture. So if that's the mean, 2.67 standard deviations, that's quite a ways away. And we want it to be more than that, so we're shading to the right. Which means that when I look it up off the table, I'm going to actually take the complement. So I'm going to subtract that from 1. So 2.67, let me go ahead and look it up off the table. 2.67, 0, 1, 2, 3, 4, 5, 6, 7. Okay, so I'm getting 0.99621. 99621. And when I subtract, I get 0.00379. Oh, I just realized this is a negative. Oops, I just caught that. Oops. So this is actually a negative 2.64, negative 2.67. Okay, so hang on. That changes things. It's still, we are going to do a complement, but negative is actually going to be over here. And okay, so here we go. We're actually shading the majority. Okay, so let me look that up. So negative 0.267, 1, 2, 3, 4. So 0.00379. And we should actually come up with the number we just got a second ago. Yep, 0.99621. Okay. So the last part, which I had to kind of go to the next page for, asked us to find the 95th percentile. So they're giving us the percentage. So the 95th percentile, you might remember percentiles are always less than that number. So 95% of this needs to be shaded. So I want to look for on the table the closest number I could find to 0.95. Okay, so I'm definitely in the wrong spot. I want to go to the positive side here. 0.95, 0.95. All right, so here we go. These are closer to 0.95. All right, so this one's pretty darn close. 0.95053, and then the one next to it, 0.94950. 94950. So that comes out to only a difference of 0.0005. I'm just subtracting them both from 0.95, where this one comes out to a difference of 0.00053. So this one's closer. All right, so that one has a z-score of 1.64. So 0.94950. All right, so on the table, the closest I found, 0.94950, and that was from the z-score, 1.64. Okay, so to find the actual mean means I have to work backwards, so that we have a formula for working backwards, which is mu plus z times sigma, or sigma times z. Doesn't matter which order we write that in. But these are the adjusted means and standard deviation. So we're using the adjusted too. So for this one, it would be 34 plus 1.64 times, I think it was 1.5. Yep, 1.5. So 1.64 times 1.5 plus 34. So I am getting 36.46. So that would be the mean associated to the 95th percentile in this example. So I'd have to get a mean of 36.46 when we're sampling, it was 100 people, I think? Yeah, 100 people, in order to say that 95% of the data falls below that value.